Okie dokie. Hi, everybody. Happy Friday. Yeah, here we go. So today we're going to be discussing section 4.2, which is about Stewart. It's about Rolle's theorem and the mean value theorem, and then we have a little quiz. All right. So first thing I want to do is I want to discuss Rolle's theorem. So that's meeting part 1. Now, I'm not going to prove this. I'm not going to do any examples about Rolle's theorem. I'm just going to illustrate it. So it's an if-then theorem. It says if f satisfies all these criteria, f is continuous on a closed interval, f is differentiable on the open interval, and the height at the endpoints is the same, then this statement's true. There is a number c that's in that interval, not at the endpoints, but in the interior of that interval, where this is true. Now remember, what that means is that the line that's tangent at x equals c has a slope that's the number 0. So I want to illustrate this. When I illustrate if-then statements, I like to have two drawings, one of the if part and then another drawing of the then part. So this says, Rolle's theorem says if the following stuff is true. I've got to have a closed interval AB. I got to have a function that's continuous on that interval and differentiable, but it's got to have the same height at the endpoint. So I'm going to put the endpoints on first. So f of A is the same as f of B. So we've satisfied the third requirement. Now to satisfy the first two, I've just got to have my function not have any breaks or jumps or missing points, and also be smooth. So I'm going to make this a little bit bigger. So here's a graph. It does all those things. It's continuous. There are no breaks or jumps. It's differentiable. That is, it doesn't have any sharp points on it. That's the if part. Now the then part is there exists a number c where there's a horizontal tangent line. So I'm going to illustrate that with another drawing. Of the exact same picture, but I want to have a separate picture so I can draw your attention to what the then part says. It says that there's got to be at least one number c. So in math, when mathematicians say there is a number c, what they wrote in mathematical jargon, this means there's at least one. So, if a mathematician says, there's a dragon on your front yard, there exists a dragon on your front yard, it could be bad, it could be really bad, it could be a whole bunch of them. So there's at least one C that satisfies this. So look, in this drawing, there are 3 numbers where the slope is 0, 3 x values. So one of them would be called C1, maybe call this one C2, maybe call this one C3. Now, the hypotheses are important. So, for example, here's a function g of x that's not continuous. It does have the same height at the endpoints, but you can see there are no horizontal tangent lines. So just because a function has the same height at the endpoints doesn't mean that it's going to have a horizontal tangent line somewhere in the middle. Or how about this one? Here's a function h that has the same height at the endpoints, and it does this. Has a cusp point. So it goes up, has a sharp cusp point, turns around, and comes back down. It is continuous, but it's not differentiable. And notice that there are no horizontal tangents. Grab a handout and sit with one of these groups. Oh, actually, there's a group of 3 there. If you join that group, it'll be a group of 4. So again, if you have a function that does not satisfy all the hypotheses, you're not guaranteed that it's going to satisfy the conclusion. So when you use one of a theorem, or this theorem or any other theorem, you have to, part of your job is showing that the function does satisfy the hypotheses. Okay, meeting part 2 is the mean value theorem. And this theorem name is abbreviated MVT. And it's also an if-then statement, and I'm going to illustrate it as well. So the if part is not as extensive. If I have the function f of x does not have to have the same height at the endpoints. So I'm going to make this function maybe higher on the left end. But I have a closed interval. And the function, of course, needs to go through those points, needs to be continuous and differentiable. So here's a nice example of a function that does that. That's the if. So the then is this. There is a number c, so at least one, that's in the interior of that interval such that this is true. So in this calculation, this is a change in y over change in x calculation. It's a slope of a secant line. The secant line that connects the endpoints, or touches the graph at the endpoints. This is a calculation of a tangent line slope at c, wherever that is. So what this equation says is, wherever there's a point c in there somewhere, where if you draw the tangent line and compute its slope, the number you get will be the same as the number you'd get from computing the slope of that secant line. In other words, this tangent line would be parallel to that secant line. So let's illustrate that in our picture. Here's my A, Here's my B. Here's my graph coming down here. So I need to draw a secant line, the secant line that contains, that touches the graph at those endpoints. So that would look like this. It's a bummer, I'm out of green chalk, so I have to use yellow. I like doing secant lines in green. So this is the secant line. And that's, the secant line slope is this number, f of b minus f of a over b minus a. So that equation says there's a tangent line somewhere in that chunk of the graph that has the same slope, so it would need to be parallel to that graph, to that line. So here's a line that's parallel. Let's move it down until it's touching the graph and is tangent. Right about there, it looks like. So this is my number C. And so the tangent line slope is f prime parentheses C, and those two things are equal. They're parallel. In geometry, you do a little thing like that. You put little arrowheads on the lines to indicate that they're parallel. So, as with Rolle's theorem, the hypotheses are important. So here's an example. F of x equals 1 over x. And let's consider just going from -1 to 1. So on this graph, at x equals 1, the y value is 1. So this is the point 1, comma 1. And when x is -1, this is the point -1, -1. Those are 2 points in this graph. So the quantity that you get when you do that change in y over change in x f of 1 minus f of -1 over 1 minus -1, that would be, let's see, 1 minus a -1 divided by 1 minus a -1. So that'd be the number 2 over 2, so that's just the number 1. This line has slope 1. But look, all the tangent lines on this graph are tilting down. So if I think about trying to find a place on the graph, well, here's a tangent line. It has a slope that's a negative number. Here's a tangent line. It has a slope that's a negative number. I'm not going to find any places on this graph where there's a tangent line that has a slope that's the number 1. So none of the tangent lines are parallel to that secant line. All right. Now I want to talk about a common kind of problem. So remember, this theorem, if it works, it just tells you, well, there's a number c somewhere that works. But it doesn't tell you where that c occurs. So here's a common type of mean value theorem problem. So given A and B and f of x, find the number C such that, or find a number C such that f prime parentheses C equals this. So you have to figure out what the number is. You can't just say, well, I know that it exists. You got to actually find the number. So the strategy is first of all, make sure that the hypotheses are satisfied. So make sure that f is continuous and differentiable, because if f is not continuous or not differentiable, there might not be a number C. So make sure or show that f is continuous and differentiable. As required. Okay. So then if it does satisfy these requirements, then we're going to be able to use the theorem. And then compute the number. Now I'm going to do this in yellow. F of B minus f of A over B minus A. That's going to be a number. And you can compute that because you know A, you know B, and you've got this function f of x. So that's the secant line slope. Okay. And then find an expression for f prime of x. So then you're going to get f prime of x equals some expression involving x. So that's not a number. It's an expression, just some expression involving x. And then replace all the x's with c's. Now I'm going to do this in orange because I don't have red. F prime parentheses C, that's going to be some expression involving the letter C. But that's really representing a number. So that orange thing is a tangent line slope. So the theorem says that there's a C that makes those two things match. So set those two things equal to each other. So set these equal and solve for C. So we're going to have expression. So f prime C, which is going to be an expression involving C. And we're going to set that equal to the number that we've already got. We've computed this number, f of B minus f of A over B minus A. So we set those equal to each other and solve for C. All right, so I'm going to try to shut up and have you all work on your drill. This is, you've got a problem mapped out to do. All right, let's go ahead and discuss this together because I want to give you plenty of time for your quiz. So what about question A? Is our function continuous, and if so, how do we know? Yeah. Yeah. I mean, it is continuous. It's a property of the square root function, but really, we've discussed the slogan that polynomials are always continuous. Rational functions are continuous at all points, at all x's in their domain. But we haven't really discussed we've discussed like the trig functions are continuous on their domain. But so, one sort of not very satisfying answer would be, yes, property of square root. But really a nicer explanation would be just to appeal to, this is just something I memorized. But if you make a graph, that would really convince the buyer. So here's the graph of y equals square root of x. Notice there are no breaks, no jumps, no holes. Yeah? Oh, yeah. Gabriel's trying to get some sleep back there, so he wants me to turn the lights down. So the key things about this graph are that there are no holes, no jumps. All right. Is it differentiable? Now, let's go back to this. What's the domain of our function? Yeah.
0 to 4.
Yeah. So this basic function is continuous for all x greater than or equal to 0. So it's definitely continuous on 0 to 4. So I'm going to say all x greater than or equal to 0, including from 0 to 4 with the endpoints. Now, how do we address the issue of differentiability?
At x equals 0 for the f prime, it would not exist because you'd have 0 in the denominator.
Yeah. So if we want to start by thinking about the graph, think about tangent lines. Okay, just in terms of the graph, this is a nice smooth graph. Imagine this is red. So, there's always going to be a tangent line with a number that's its slope. Since there's always a tangent line with a number that's its slope, the derivative always exists. Except here, if we had a tangent line thing, it would be vertical, vertical lines have undefined slope. So it looks like this graph is not differentiable at x equals 0. Well, let's see how that's borne out in the formula. F prime of x is the derivative of square root of x. That's 1 over 2 square root of x. So this exists for all x greater than 0. It does not exist when x equals 0. So in particular, it exists for all of the x's that we care about, the x's in that open interval. All right, so we've satisfied the hypotheses. Now let's get going a little faster. I do have a green pen. So our secant slope is going to be m secant. It's going to be square root of 4 minus square root of 0 over 4 minus 0. So that's going to be 2 over 4. So that's the number 1/2. And then we have f prime of x is 1 over 2 square root of x. So if I put in the c, I turn it red because then it becomes a number that's this tangent line slope. Okay, so now we set those two things equal to each other. 1 over 2 square root of c, that red number, has to equal that green number 1/2. So you solve this, clearly that number, that square root of c must be the number 1. And c has to be a positive number because it's got to be in the interval from 0 to 4. So c must be the number 1. So we found our c. Now, so textbook problems might just say find the c that works. Find the value of c that satisfies the conclusion. And you'd be done. You could go home. But, you know, in this bizarre class, I always make you illustrate things, and then I give you quizzes, so you can't go home. But let's draw our picture. Here's our graph of y equals square root of x. It goes through the point 4, 2. It goes through the point 0, 0. So our secant line looks like this. So m secant is the number 1/2. And our number c is 1. So if we go to the graph at that point and draw the tangent line has also slope 1/2. Isn't that pretty? Okie doke. So if you would please get into alternate seats. During your quiz, I'll be putting out the graded exams. I really enjoyed reading the exams.